Alright, so far we have look at the locus representation in the form of a circle and also perpendicular bisector of the variable complex number z. Right, so let's take a look at the circle again. Now the variable complex number z, alright, represented by the point P. Here's my point P. And the fixed complex number P plus Qi is represented by the point A. Now in this equation, we understand that the distance between P and A is always K. Right. For the perpendicular bisector, again Z is represented by the point P, and we let the point A represent the fixed complex number P1 plus Q1i. Here is P again, and the complex number P2 plus Q2i is represented by the point B. Now I've done a bit of mistake here. The I should be inside. Okay, let me just rectify that. P2 plus Q2i, yeah. So P2 plus Q2i. Okay, so that's the correct one. Alright, so for the perpendicular bisector, okay, from the equation, what we are saying is the distance between P and A, alright, is exactly equal to the distance from P to B. Now, because the Argand diagram is very analogous to the Cartesian coordinate system, alright, we can use vectors to represent what we are looking at now. So if you were to look at this as vectors, you're looking, okay, for example, at the circle, it is the modulus of the vector AP. Alright, and this modulus is always the value K. Right, and then for the perpendicular bisector, we are looking at the vector AP, right, and BP. Okay, so if we look at the analogy of a vector, right, the modulus of AP, the vector AP, is always K, where for the circle, whereas for the perpendicular bisector, alright, we are looking at the modulus of the vector AP and the modulus of the vector BP, which needs to be the same every time. Alright, and this makes sense because from what we have seen in the circle, it is exactly so, and what we see in the perpendicular bisector, it is also exactly so. Alright, now the third locus that we're looking at is actually called the half line, which I'm going to introduce to you in a short while. Alright, so it is important that we recap the circle and the perpendicular bisector as what we have seen in the original form, and also in the form that we will see now in the vector form. Now before we proceed into the idea of the half line, alright, now it is important for me to stress upon you the difference between the meaning of angle and argument. Alright, so please take note that whenever we use the word argument, we do refer to some kind of angle, but we also refer to the direction in which the angle is being measured, either clockwise or anti-clockwise. And also when we talk about argument for complex numbers, we would like to present our answers for the argument in the standard form, which actually the argument lies in the principal range, which is between negative pi not included up to pi included. Alright, which is what I will state here. If theta is the argument, so the principal range for theta is actually between negative pi not inclusive and pi inclusive. Right, so this is the principal range. So the half line has an equation which is of this form. Alright, the locus of the half line, okay, from the point A, excluding A, right, where A is a point representing the fixed complex number A. So usually we also define A to be in the form of P plus IQ. So I can actually write the equation of the half line in this way: argument Z minus P plus IQ, alright, equals to theta. So I can also write the equation of the equation representing the half line in this form, yeah, where Z again, right, is represented by the point P, and P plus IQ is represented by the point A. Alright, now as I've discussed previously, if you were to look at the circle and the perpendicular bisector as vectors, right, so we could also look at the half line, okay, as if I'm looking at the vector. Alright, so how so? So the argument of Z minus A equals to theta, I can actually look at the argument of the vector AP, alright, which is in particular the angle that the vector AP makes with the positive real axis. You will see later in more difficult examples it is easier for us to actually make use of this vector concept, alright, to determine the argument, alright, defined by such an equation. Okay, so the half line, as I've just said, alright, is the locus of the half line point A, excluding A, where A is a point representing the fixed complex number A, that makes an angle theta with the positive real axis. We shall look now into actual examples on how the locus is actually defined, alright, in terms of the half line.